Welcome to the AI seminar for today. My name's Tom Dietterich, and I recently got back from spending about a month in Beijing as a short-term Fulbright visitor. I was there at the request of the State Department to do various events on robust AI and AI ethics. But I also gave a 4-lecture short course at Tsinghua University. They were my hosts. And so this is based on, the theme of the 4 lectures was, when can we trust the outputs of a machine learning system? So if we're using machine learning in a high risk application, we certainly want to know when we can trust it and when we can't. And so this first lecture is about trying to get what are called calibrated probabilities from machine learning models. So what do we mean by a calibrated probability? Well, I'm going to use this notation to say this is the probability given input x, the probability that's estimated by, say, a neural network or something, that the correct output is y. So this would be for standard supervised learning. We're really looking just at classification today. And this is somehow the true distribution, true conditional distribution, p of y given x. So we get something that comes out from the learning algorithm and something that's true in the world, and we want those to match. So, probability calibration has been studied for a long time. It sometimes shows up in the popular press when people talk about weather forecasts, right? And the weather forecaster says the chance of rain tomorrow is 80%. And what that means to be well calibrated is that 80% of the time that the weather forecaster says that, it does in fact rain. Right, so that's this idea here. So it is a deeply frequentist notion of what it means to be correct. Well, why do we care about calibrated probabilities? Very often, for instance, we could just get some sort of a measure of confidence out of a classifier. For instance, the margin in a support vector machine, and we could just determine a threshold that is high enough and only trust it if it's higher than some threshold. I think there are several reasons. One is if we want to do rational decision making, for instance, in a situation where our costs are unequal. So if L of k prime is our loss function or our cost function, when the right answer is k and we predict k prime, then the expected cost of predicting k prime is just taking the expectation with respect to that distribution. Right? And so if we can plug in a well-calibrated estimate of this, then we get a good estimate of the loss. So we can make our decisions in a cost-sensitive way. We often may have additional decisions. In addition to saying, oh, the class of input x is 1 or 7, we could also abstain. Or we might have other actions we can take too, like, I don't know, calling our mother or something. And if we have another action, we can add that to our loss function here. This is the loss of abstaining when the true answer was k. And then again, we can say, well, what is the action that minimizes our expected loss? And so we can use this to decide to make a rejection decision in a rational way. Another reason is interpretability. If a support vector machine says, well, I think it's class 5 and the margin is 3.2, it has no semantics. But it's some distance in some kernel space or something like that. But here maybe people can understand a probability statement like that we think the probability of y equal to k is 0.8. I saw something recently on Twitter that said people only understand 0, 1, and like 0.5 or something. But at least those of us with some training, we can understand what this might mean. A third reason is system integration. So very often, right, our machine learning component is some part of some much larger system. Even the biggest machine learning intensive applications, in terms of lines of code, I think the machine learning part is maybe 10%, right? So there's a lot of other things typically going on in these systems, and it's easier to integrate multiple machine learned subsystems into a larger system if they're all working with well-calibrated probabilities. So in particular, things like fusing of multiple sensors, combining evidence from multiple sources, things like that. A fourth reason is improved accuracy. Now this is a little counterintuitive to me because I always figured that we could do what I was saying. If we were getting some confidence score out of our classifier, we could just threshold it and we'd be okay. But here's an example, a counterexample from Cohen and Goldschmidt. I'll give citations at the end. They said, well, what if you have data that consists of two classes, but the red class is actually bimodal, and you're fitting a linear decision boundary to try to separate the red from the green. And so the optimal or the uncalibrated boundary might be this red line here, which means it's going to misclassify all these points over here. But we can calculate something called a calibration curve, which I'll talk about in a minute, which in this case is highly non-monotonic. And by recalibrating, we can actually improve the accuracy of the classifier. So it'll be clear later how we might do that. Another example would be data like this. Again, if we fit a linear support vector machine to this data, we're going to get some kind of a decision boundary that's going to do something like this, right? So it's going to get maybe all the red ones right, but a lot of blue points wrong. And the area under the ROC curve for a support vector machine with a linear kernel is 0.52, so barely better than random guessing. But after calibrating it, we can get it up to 0.65. So that's an example of where we can improve accuracy. In general, if you think about the simplest case of just a two-class problem, right, then typically we say, well, which class had the highest probability, right? That's our decision. But that's equivalent to thresholding at 0.5. And so with calibration, we can find out where the true 0.5 is instead of just taking the whatever the machine learning algorithm gave us. In multi-class problems, the effect can be stronger, especially for rare classes, because those are typically very poorly calibrated. But if the estimated probability is monotonically increasing with the true probability, then we won't improve accuracy at all. We'll just be cleaning up that monotonic relationship, but we won't improve accuracy, provided we choose our threshold carefully. Okay, a great way to visualize what's going on in a classifier is to produce something called a reliability diagram. And these were developed in statistics long before computer scientists came onto the stage. So what we do is we're going to train our system on some training set of points, and then we'll have a held out calibration set. And what we do is we take the unit interval, let's say, and divide it into m bins. So typically they divide it into 10 bins. And then for each bin, let's let big B sub little b be the set of points whose probability scores belong to that bin. So these are all the points for which the classifier said the probability of, say, of a positive example was between 0 and 0.1, 0.1 and 0.2, and so on. So these are the ones it was very confident about. These are the ones it was very not confident about, right? And then for each bin, we can also look at our calibration set. So then I'm getting ahead of myself. Then p hat of big B, little b is going to be the average predicted probability for those points. So it'll be somewhere in the middle. It's not necessarily in the middle of the bin, but we're plotting it here. And then big P hat is our estimate of the population. So this is the fraction of our predictions that were actually correct according to this calibration set. So this is an estimate of a Bernoulli value from the calibration set. And so we can plot them like this. In this case, this was for the adult data set, and it's fitting a naive Bayes model. And naive Bayes models are known to be quite poor. They generally are quite extreme in their probability predictions. So you can see here that when the naive Bayes model is predicting a value in the 0.9 area, its true accuracy is something more like 0.78 or something like this, right? 0.77. And when it says it's between 0.8 and 0.9, well, it's really around 0.5. So its predictions are optimistic, and that's why all these points are below the diagonal line. It's a little bit pessimistic here, or pretty well calibrated down here at the bottom. So these are the number of points that were used to estimate each of those those stars. So we often summarize this in terms of a calibration score, which is the squared difference between the predicted value and the observed value, right? And we like that square difference because it relates to something called the Breyer score. So, you know, in the theory of loss functions for supervised learning, there's this notion of a proper scoring function. So log loss is a proper scoring function. Turns out squared loss is also a proper scoring function, even if you're fitting 0, 1 outcomes, right? And in particular, that's also known as the Breyer score. So it's the sum over our training examples I, or our test examples I, of the predicted probability of the predicted output minus an indicator function whether that predicted output was correct or not, right? And then we square those and sum them up. And you know, we love square type losses because they usually decompose. We know how the sum of squares decomposes into various things. Well, it turns out the Breyer score, you can also decompose it into one term here, which involves the square difference between the probability scores. When we impose bins on things, then we get the sum over the bins of the probability that a data point falls into bin B times this square difference, which is the calibration score, the calibration error. And this term, which is something like the weighted variance of the ground truth, which is known as the refinement score. So the second term is going to be minimized when our predictions are very close to 0 and 1. So a classifier that minimizes the sum of these two terms is well calibrated because the first term is close to 0. And it's also very confident, so the second term is close to 0. That's our ideal classifier, right? It's well calibrated and always right. That's what we'd like. So we can see that the calibration score is part of this Breyer score when we bin things, and which is nice. Okay, so but it is important to point out that you can get improved calibration without having a very good, without improving refinement. In other words, you can improve the first term of this while leaving the second term unchanged or even making it worse. And for instance, if 70% of your calibration points belong to class 1, then you could just always predict class 1 and just set your, with a probability of 0.7, and then you'd be well calibrated and useless, of course. So, and our refinement score in that case would be 0.21, so it would be pretty large. So I guess coming back to this again, so what's the worst possible Breyer score? Well, that's when we sort of output 0.5 all the time. Well, I don't know what that would really mean over here, but that would maximize this, this term here. Okay, so how can we actually achieve calibration? Well, it's actually fairly simple in some sense. I mean, if we go back to this thing here, we're basically going to investigate a series of models that try to model this curve, right? And then replace the predicted score by the true score over here, right? So basically, we're going to fit a model to these points. We don't actually fit it to these binned points. We can go directly to the raw data, but it's hard to visualize the raw data because it's all zeros and ones. But we can sort of think of it as we're going to fit some kind of a model to this reliability diagram, and then use that model to correct the predicted probabilities and turn them into well-calibrated ones. So the first method is to do exactly that. We're going to bin the data, and so if we use fixed width bins, for instance, then we can sort the data by its predicted probabilities for its output, and then estimate the true probabilities for each bin, and then define this function g to be the true probability, as estimated from our calibration data, the true probability for the bins that contain probability scores that belong to that bin. We can either do that with fixed width bins, or we can, which are fixed width in the probability scale, or we can define bins so that each bin contains, 1 over m of the training data. So they might be variable width, but they would each contain, say, 10% of the training data. So that's the very simplest thing. And so in that case, we would just, as I say, we'd replace when instead of outputting 0.5 at these points, we'd be outputting 0.32, and in this range, instead of outputting numbers between 0.6 and 0.7, we'd be outputting 0.35 or something. So it's a piecewise constant function that we have fit to transform these predicted probabilities into calibrated predicted probabilities. Another thing we can do is something called Plat Scaling. So we can basically take the predicted probability or predicted score and fit a two parameter logistic regression model to it, right? So this has been given the name Plat Scaling because John Platt published a paper on trying to take support vector machine outputs, right, which are on a score that's related to the margin, the geometric margin of the data, and he noticed that the reliability diagrams for these are really well fit by a sigmoid. So he just said, well, let's use standard logistic function. So he, with some slight tweaks, he basically fits a logistic regression to the calibration data. So you can, for each data point, there's essentially one predictor variable, which is the SVM score, and then you're trying to predict either 0 or 1, which was whether the prediction was correct or not. And so, and that's your logistic regression model. So this is known as Plat Scaling, and it's due to Rich Caruana, who later wrote a summary paper citing this. And Platt complained that which got tons of citations. This paper is extremely highly cited, right? A very simple idea everyone can understand. And John Platt complains that of the many, many interesting things he's done in his career, this is going to end up being the thing that he's best known for: one variable logistic regression models. So Platt's now, so Caruana actually will be visiting and giving a talk here in February, I believe, early February for the EECS colloquium. He's at Microsoft Research now. And Platt, I think, is at Google maybe, but working on nuclear fusion now with machine learning. Okay, the third method is isotonic regression. So the idea is, it's been known since 1955, the idea that suppose I've got a set of points, I believe it is a monotonically increasing function, and I want to fit a monotonically increasing function to it that minimizes the squared error between the fitted function and the data points. And it turns out there's a very efficient algorithm called the pool adjacent violators algorithm, and that the optimal solution is a stepwise constant function. So so this is what happens if we fit an isotonic regression model to this. So you can see, in some sense, it's kind of an adjustable binning model. All the points in this range here, right, are all binned together, and we're going to predict this probability over here, right? Here's a little tiny bin, we're going to predict that probability. Here's a very tiny bin, we're going to predict that probability, and so on. So the number of bins is determined by how much merging it has to do to force the function to be monotonic. So this is the algorithm, pool adjacent violators. And the basic idea is our input is our predicted probability for the ith calibration example, and yi is really 0. Let's assume it's a binary Boolean problem. So, but yi is the correct answer. Then what we do is we initialize a set of trivial bins. MII is a bin that only contains point yi, and so it has a weight of 1 for each bin. And then if we look for a pair of bins that are adjacent, I minus 1 to I, because we've sorted them, but where the value of this bin is bigger than this bin, which violates the monotonicity property. And when we find that, we merge those two bins into one, which involves this weighted merge and also summing the weights. And then that new bin replaces those two. And we just keep doing that in any order we want. So it's an example where the greedy algorithm really finds the optimal solution. So, and then we're done. So it's a very simple algorithm. The fourth method we might want to consider is something called regularized isotonic regression. So a challenge, it's interesting to think about each of these models and how many degrees of freedom it has, right? So here we have, if we're doing m bins, we're going to have m degrees of freedom, right? If we're doing this, we really only have 2 degrees of freedom. If we're doing this, ooh, the number of degrees of freedom could be quite large, right? And so the idea of MPAVA, this came out of a Hasty Tibshirani paper a few years ago, which in the style of these Stanford Statistics Department papers, they love to do the complete regularization path. So what they do is they say, we can think of isotonic regression as the solution to this kind of relaxed problem. So the first term is our calibration error, and the second term is this is an indicator that says, ooh, we have a violation of monotonicity, right? And this is sort of how big that violation is, right? And so we can think of lambda as the regularization parameter. If we set lambda to infinity, then we want to have no violations, and we get back the original PAVA algorithm. But if we set lambda to 0, we don't care about violations at all, and we just minimize this, and we get a trivial solution. So, but the interesting thing, of course, is we can find all of the distinct values of lambda that make any sense along the regularization path from 0 off to infinity. And so this is a nice efficient algorithm that produces a sequence of, say, near isotonic regression models. So a student named Naini, working with Cooper at Pitt, has a very recent paper called Ensemble of Near Isotonic Regressions, where they take a weighted average of these isotonic regressions weighted by their BIC scores, normalized, to try to deal with the overparameterization. Okay, and then there's a minor industry in other flexible models. So people have tried splines, piecewise linear functions with a tree-based decomposition, Gaussian processes, inevitably. And I actually have another idea. But in any case, it's not obvious that we need them. We'll come back to, we'll look at the experimental evidence in a little bit. But what about when we have, that was all just for 2 classes, just for binary problems. What do we do when we have K classes? Well, a simple thing to do is to define capital K binary classification problems, right? Where each one is trying to treat one class versus all the rest of the classes. So we train a set of separate binary classifiers, and we learn a calibration function for each of them, just the way we were just describing. And then we basically take those calibrated probabilities for the individual one versus rest and just normalize them so that we get a discrete distribution over all the K outcomes. So that's one simple strategy. Another idea is to tune the softmax temperature. So right, in machine learning, we talk about the symmetric multinomial logistic function. We call it the softmax, right? And so we basically have logit scores z1 up to zk, which are on a real valued scale, right? Something like the logits of the different possible classes k. We exponentiate them and then normalize. And but I've written this with a model that has an additional parameter in it, a temperature parameter, which we usually set to 1, right? And this is what we use in all the neural networks and just about everything else. I mean, symmetric multinomial logistic regression, you would normally set t equal to 1. And so we'll abbreviate this function as sigma softmax, and we can write it as the vector z divided by the scalar t. And we'll see that this actually is sort of a 1-parameter version of Plat scaling. Works quite well. But people have also looked at matrix scaling, where we learn a matrix W and an intercept vector B, and we transform the scores like this and then push them through a softmax. Or simple vector scaling, which we force this matrix to just be a diagonal matrix And in that case, we really are sort of fitting a bunch of logistic functions for each class. Okay, so let's go through what's been known experimentally in the literature. So the first paper that is of note is by Niculescu and Mizil and Rich Caruana back in, I think, 2005. They have many insights. I really love this paper because it was a purely experimental paper, but they have beautiful visualizations that you'll see in a moment, and they really thought carefully about what was going on. So it was much different from the standard, run a bunch of experiments, sort the algorithms by their scores, and you're done. They were really trying to understand what's going on. So among their insights are that machine learning algorithms that are sort of maximum margin algorithms tend to push their predictive probabilities close to 0.5, whereas naive Bayes tends to push its predictive probabilities close to 1.0, so quite extreme. And basically, calibration flattens out those distributions, so it pulls them back towards something that's more like a uniform distribution. It seems that the max margin methods are fit well by a logistic regression, and so they need relatively little calibration data to fit that model. Isotonic regression, but logistic regression doesn't fit the naive Bayes behavior very well, this kind of extreme behavior. So you need to use isotonic regression in that case, but that usually requires quite a lot more data because you have so many more degrees of freedom. So those are the main conclusions of their paper. But here's some of their plots. So across each column corresponds to one data set. So this was cover type, which is a remote sensing data set. The adult, I think income from the census, some letter recognition problems. I don't know this METIS data set, Slack, and then I can't remember what the other two are, HS and MG. I don't know. Anyway, and then what you're seeing here is this is a histogram of the uncalibrated scores. And this is all for boosted decision trees. So if we think of something like XGBoost or one of these boosting algorithms, this is the kind of behavior that you see. And so they pointed out that, for instance, this is a good example where the probabilities are in from, it rarely predicts 1 or 0, right? It's sort of in the nature of these boosting algorithms that they can't predict the extremes because they're averaging over multiple models. And you can see in this data set in particular how the scores are all bunching up toward the middle. Some of the other data sets have very skewed class frequencies, so the middle is more like 0.1, but it's still around the kind of average score. And so these are the reliability diagrams plotted with a fitted sigmoid on them, and these are the same diagram, but now with a isotonic regression on them. So you can see, first you can see that they're very far out of calibration, right? Which way are they failing? Let's see. They're pessimistic up here, right? So their true calibrated probabilities are high even when they're predicting low values, and they're optimistic at the low end because they've squished things together. And so these sigmoids fit pretty well, maybe not so well here, but maybe not so well over here. But even this, this is a pretty pathological fit there. I had to create a very big bin at the high end. Anyway, so that gives you sort of a sense of what's of things there. And here's the boosted trees after using the logistic regression, the Plat scaling. So now we can see that like this distribution for the Slack data set, right? Before it was really bunched up, and now it's pretty much flattened out. And you can see that this is true for these HS and MG data sets too. Now they look much more U-shaped, which is what we would like to have, right? And that means the classifier is really good if it's calibrated, and it's also generally very, very confident. Hard to understand the adult thing because it's somehow the responses are discretized. I can't remember why. But things are much better calibrated. And here's after applying isotonic regression, The scores are even better calibrated, but the histograms are now, because it's all bins, the patterns are less clear. And then they compared 10 different learning algorithms all on that Slack data set. So we've already seen this plot here, right? Where for boosted decision trees, it looked like this, we fit this, we get this. But then this is for boosted decision stumps, right? So a tree that is only allowed one test and then makes its predictions. It's even more peaked in the middle, and again, we get something that's much more flattened out. This is a support vector machine, which again is very peaked in the middle, is well fit by the sigmoid, and we get the scores flattened out. But then when we come over and look at these things, like this was an artificial neural network. So this was, again, 2004 or 2005. So they were using, I think, a single hidden layer, we would say, a multi-layer perceptron. It's already pretty well calibrated, right? The Plat scaling doesn't really help necessarily. The isotonic regression is also pretty boring, and the distribution afterwards, if anything, may have done some damage, right? Because it's pulled in from the edges a bit. And maybe the same is true here. This is logistic regression. And I should note, right, in theory, the log loss, which we're optimizing for logistic regression and in theory for artificial neural networks, it is a proper scoring function. And so the theory says that what makes a proper scoring function good is that the predictive probabilities will converge to their consistent estimates of the true probabilities. And so we sort of, when you see this, you say, well, of course, these guys over here are optimizing some other weird stuff. These guys are all optimizing a proper scoring function. They're getting well calibrated. Those guys aren't. It looks like it should. But we'll see that with deep neural networks, we're also optimizing a proper scoring function, and we're getting very poorly calibrated probabilities. So I guess I already said all these things. And here's a few more algorithms. So this is a single decision tree at the top. This is a random forest model, which, random forests also have difficulty being confident because some of those trees will be bad, and they'll pull the average in away from 0 and 1. So after recalibration, it's a bit flatter. This is a k-nearest neighbor classifier, and this is naive Bayes. And so in the naive Bayes model, you can see that it's poorly calibrated, but in a way that makes the sigmoid function not fit very well. And after calibration, it's still kind of a mess. So I guess that was the only point there. Then another thing they asked in the paper was, well, how big does the calibration data set need to be? And so these are sort of learning curves varying the size of the calibration set. And the vertical axis is, oh, I wish I knew, maybe our calibration error. Let's guess that it's a squared calibration error. And of course, this is if we don't change it. The line isn't quite flat because any points that didn't go into the calibration set were put into the training set. So as we move to the right here, we have less data for fitting the model because we're using more data to calibrate the model. So that's why that red curve is slightly dropping. But that's the unscaled or uncalibrated performance. And then this is using isotonic regression, and this is using Plat scaling. So we can see that in general, as we'd expect, because Plat scaling has many fewer degrees of freedom, it converges, learns faster. But maybe out here, it's not maybe. I don't know. I think there are error bars on here, yes. But maybe it's doing slightly worse than out here because it doesn't have as many degrees of freedom as the isotonic regression. But it's looking like for Plat scaling, maybe 500 calibration points is enough. I mean, it depends on the number of classes too, presumably. But for isotonic regression, maybe we need 4,000 to 8,000 data points instead, at least on this particular data set. Okay, well, the second set of experimental results I want to report is from this very recent paper that came out just the last year by Guo, Pleiss, and Sun and Weinberger. And they were looking at this very large neural network called ResNet. It's a residual network, which has a kind of boosting character to it, right? It's in effect a kind of linear. Well, it's a pipeline of residual units, but those units have shortcuts around them. So it's possible for the model to only use as many of those residual networks as it needs. And there's been an analysis of ResNets that suggests that they're a bit like boosting, in that you initially learn the model without using any of them, and then you fit each of these residual units to reduce your residuals, much like a boosting algorithm does. And so these guys have kind of these are their reliability plots, which are not very easy to read. But they're comparing to LeNet, which is, I think, was one of the early character recognition networks and has only 5 layers. I think maybe 2 convolutional layers and then 2 fully connected layers, something quite simple. And it's actually fairly well calibrated. We can see here. It's a little optimistic up at the high end, but it's not too bad. This is a histogram of its predictions, and it's also not terribly accurate, right? So it has a 45% error rate on this data set, which is the CFAR 100 image recognition data set, so 100 classes of images. It's a pretty challenging problem. Now, ResNet is much more accurate, right? It still has a long ways to go, but it's, say, 31% error. But look how optimistic it is. It's predicting, probability 1 when the real answer is, I don't know, 0.9, and probability 0.8 when the real answer is, is something like 0.4, right? This is its prediction. So they've visualized the gaps, which is the absolute miscalibration error. So what to do about it? Well, they first wanted to understand, well, what's causing it? So you can vary, they explore various parameters in the paper, but I'm just going to look at these 3. One is the depth of the ResNet. How deep, how many residual units should you stick in there? Determined, summed up in terms of the total number of layers in the network. This is sort of how wide you make the network. And this is whether you're using batch normalization or not. And batch normalization, right, seems to be very important for fast learning and for accurate learning, but I'd say we still lack a good theory about exactly what it's doing. So what they're reporting is they call error is actually not the calibration error, but the sum of the absolute calibration errors, right? This thing here, ECE, the mean absolute calibration error. And I'm not sure why they chose that. It doesn't relate to any proper scoring rule as far as I know. But anyway, what we see is that the calibration error if the network is shallow, it's pretty low, but it grows as the network gets deeper. It also grows as the network gets wider. And then it also grows with batch normalization somewhat. So batch normalization definitely makes and we also see, as other people have observed, that the deeper networks are more accurate. So this is somehow the 0-1 loss. And wider networks are also more accurate. And batch normalization is improving our accuracy too. And this is looking at weight decay, right, which is basically L2 regularization on the weights in the network. And we can see that using larger, this is the value of lambda, the regularization parameter, and as we make it bigger, our calibration error improves, but our error 0-1 loss also increases. So sort of the best place here is going to have a significant calibration error. So they argue that there's something about getting high accuracy out of these deep nets that also causes the poor calibration. So they then compared, so then they proposed these temperature scaling, vector scaling, and matrix scaling for trying to scale the probabilities coming out of the softmax layer. And this is my plot from their table. So hopefully I didn't screw anything up. But I sorted this they were combining various data sets and various models. And so the red curve here is where they're just scaling the temperature of the softmax, and it gives just about the best performance on every data set. The green ones are if you use a vector scaling, so that's using just a diagonal, that's sort of a separate softmax for each class. Or I mean a separate logistic regression curve for each class. This is matrix scaling, which we can see is sometimes just fine, but often has very, very high calibration error, and is completely missing for some data sets where it was too expensive to compute. And then this is the uncalibrated scores, so they're much higher. So the conclusion from their paper is temperature scaling is really good, and in fact, if you look at vector scaling, it generally uses a diagonal matrix where the diagonal entries are almost all identical. So it's discovering temperature scaling as well. I'd be interested to know whether they didn't do temperature scaling initially and then they noticed this and said, oh, maybe a one parameter model would suffice. And then this is comparison against a few other methods. So again, this is the uncalibrated curve. This is isotonic regression, histogram binning, and this is temperature scaling. So sometimes isotonic regression wins a little bit here, but again, this temperature scaling seems to be quite robust. So, so the simple temperature scaling calibration model seems to work well and work better than more complex generalizations. They also talk about in their paper that this temperature scaling calibration can be derived as a solution to a maximum entropy optimization problem. That is, this will be our calibrated probabilities, p hat. We want to maximize the entropy of that distribution subject to two constraints. First, that it is a probability, so the entries are all non-negative and sum to 1. And second, that the sum of the true class logits is equal to the mean value of all the logits weighted by their p hats. And I'm not sure what that constraint means, but if you adopt that constraint, then temperature scaling is the answer. So at least we know if temperature scaling is the answer, what was the question? This was the question. One thing they didn't do is compare against Plat scaling each class separately and then normalizing, which seems like would have been another reasonable baseline, but might have been basically the same as their vector scaling. So then the third paper of experimental results is this ensembles of nearly isotonic regressions. So they were quite thorough. They had 40 data sets from the UC Irvine collection and the Lib SVM collection. They compared naive Bayes, logistic regression, and support vector machines, so they were not particularly adventurous in the classifiers. And they tuned their hyperparameters by cross-validation. And then they compared isotonic regression and then a previous method of their own called Bayesian quantile binning, which was ensembles of different binning models. And then this new method, which is this ensembles of these models generated by the full regularization path of the near isotonic regressions. One complaint I have is that they reuse the training data to do the calibration, which, I mean, on the one hand, economizes on data, but it should give you biased estimates, and you'd probably get better calibration using fresh data. And they didn't really compare against model-based approaches like Plat scaling. But they look at several metrics. So they look at the accuracy of the classifier before and after calibration, which we would expect maybe not to change too much. They looked at AUC, which we also might expect to not change too much, because AUC, unless the original reliability diagram was non-monotonic, the AUC shouldn't change at all, right? Because calibration is kind of moving around the probability, but it's not changing the order in which the rankings of the points. So, and AUC is really just a ranking measure. They looked at the square root of the calibration score, and then the expected absolute calibration error, and also the maximum absolute calibration error, which is perhaps not so meaningful. And so then they report confidence intervals on whether the change made any difference across those 40 data sets. And so let's see, what's to note is that for logistic regression, the AUC is not, the confidence interval spans 0. Same for the SVM, and same for naive Bayes. So no change really in the AUC. The accuracy for logistic regression does improve a little bit, and for naive Bayes improves quite a bit. And the squared calibration error definitely drops, right? So these are all measures of improved calibration, and they improve hugely. They get smaller, which is great. So the calibration metrics all improve. So we are doing a good job of calibrating. And then if we look at logistic regression, and they report the average rank of the different calibration methods for each of these things. So if we apply, say, this ensemble of near isotonic regressions and to each of the data sets, and then we rank them by their AUC, then what we find is that the ENIR method gives is usually has a rank right there. There are these 3 methods. So I guess the rank sum to 3.
Pretty much. Yeah.
Right, average rank of the calibration methods using logistic regression as the Bayes classifier. Yeah. So this generally works well compared to the other 2 methods, but the stars are the only ones where they could where they were able to reject the null hypothesis that there was no change. Let's see, right. And then this is for support vector machines, and which is kind of the same answer, which is that the trend is good, but there are very few significant differences. And for naive Bayes, the trend is good, and there are a few more significant differences because naive Bayes is so bad. So the insights, I think, from this are using the regularized version of isotonic regression does not improve the accuracy or the error under the ROC, or the area under the ROC curve compared to regular isotonic regression. So they didn't really get a win there, but they did get better calibration. But my main criticism of the paper is that the main advantage of regularizing should be to reduce the effective number of degrees of freedom of the model. And so it should require less calibration data to calibrate. But they didn't do a learning curve analysis of how much calibration data you needed. So I think that was where maybe they could have seen a real benefit from their technique. So, yeah. So I guess just to summarize then, and I think these conclusions pretty much derive from the Niculescu-Mizil-Caruana paper, is that the maximum margin methods like support vector machines and boosted trees, the predictive probabilities tend to concentrate near the middle, which gives us a sigmoid-shaped reliability diagram, and then a logistic regression model fits well and learns quickly. For naive Bayes and deep nets, the probabilities concentrate near 0 and 1, and are systematically optimistic. So isotonic regression is probably better, but temperature calibration worked extremely well for deep nets. So there's still, I would say, a kind of mystery about what's going on there. And the trouble is with 100 classes, it's much harder to visualize whether the calibration is benefiting some classes versus others. They need to write a longer paper and go into do more careful experimental evaluation. And then for random forest bagging and multi-layer perceptrons, they were naturally well calibrated except at the extremes. The sigmoid model fits poorly, and you need a lot of calibration data before you will see any improvement over just going with the uncalibrated model. So that's pretty much all I have to say. A few closing thoughts is, when we're doing this calibration, we're trying to be accurate everywhere along the whole probability scale. And I guess an interesting question is, do we really care equally about all parts of that space, right? If we're going to use the calibrated scores just to make a rejection decision and say we only want to believe the classifier when we think it's correct, it's very likely to be correct, then we really only care about the very large values of p hat, and so we could just calibrate for that end of the scale. Or if we're doing anomaly detection and we're very interested in the rare events, the low probability events, maybe we only care about the very small values. Or maybe we're doing something like stock market trading where basically predicting anything above 0.5 is you're going to make a lot of money. So maybe we're just concerned about that part. We don't actually expect there to be anything at the high end of high accuracy. Low accuracy probably can achieve that, but the highest accuracies are going to be close to 0.5. So I don't know. I mean, we have this principle in machine learning, which is that called Vapnik's principle, right? That we should only solve the problem of interest and not a harder problem on the way to solving our problem of interest. And so maybe getting good calibration over the entire probability range is that harder problem, and maybe we should focus our attention on exactly what we need for a particular application. On the other hand, if you are training a module and then you're going to release it or put it inside some other systems, you don't know what that ultimate application is, so then you do need to calibrate over the whole range and leave it to the end user or whatever, the downstream processing to decide where they want the thresholds to be. So, and here are my references. I slightly fixed it for today, but the old version of this is on my website, so you can go look at all these. But I especially recommend this Niculescu-Mizil paper from 2005, because I think it's a good example of experimental research that is not just an evaluation exercise, but is really trying to understand what's going on. And they really did a great job there. Okay, I'll stop and answer questions. Thanks. Yes.
I guess, thanks. I did read this Nicolas Mizell paper as a PhD student.
Right.
Yeah, and we were kind of looking at calibration at that time. It was mainly for boosting, but anyway. So, question really is, I think a lot of this problem, especially in practice, for calibration problems often come together with some kind of either covariance shift or domain adaptation or some kind of any case where testing distribution would potentially be a little different from the training distribution.
Right.
So in computer vision practice, a lot of times we see, we kind of work pretty hard to calibrate really well on the validation set, but then on the testing set, it's a totally different threshold than they're supposed to use.
Right. I mean, if you had some labeled data from the new distribution, you could recalibrate for that new distribution without retraining the classifier, which would be kind of small version of transfer. But
right, and then in practice, also the other thing is if you're gonna use for example the last example you mentioned, the shifter machine learning or computer vision module for use in a much larger world, it's almost certainly gonna be some kind of domain adaptation where your so I think it's kind of an interesting problem to study whether your pre-calibrated probabilities will be okay under this more adversarial distribution, testing distribution.
right, or I definitely feel like an open research question is in domain adaptation and also in few-shot learning, how can we get well-calibrated probabilities in those cases? Can we somehow transfer our calibration knowledge also across somehow? So that's I'd say is an area ripe for study. Yeah, I don't have any good ideas about it, but I mean, at a minimum, we should evaluate how well calibrated are current, say, one-shot learning methods.
Oh yeah, I think I remembered something previous supervisor guy Lebanon was doing is based on how many positives you're supposed to see, and so treat that as an invariant between the training and testing sets and so on. Which may not be the perfect idea, but it's a different ways, right? So if you're kind of transferring, so if you kind of assume your conditional, if you're kind of assume your marginal px is going to change a lot, right? Maybe still, because of their conditional, then the amount of positives and the amount of negatives in
Right.
the testing set.
So your class frequencies,
Yeah.
I mean, yes, in some sense, if we go to all the trouble of training a classifier, then we need some way of getting assurance that our test data come from the same distribution. And what are things we can measure about our data that might give us confidence for that? And so we can look at all kinds of things, right? Marginals, and we can also look at the distribution of our predicted probabilities. In my Steps Toward Robust AI talk, I mentioned this work in speech recognition where they look at the class proportions of the phoneme predictions. I think it was the phoneme predictions. It might have been, and just say, well, those should be, if they were more concerned about that there would be some frequency band that was corrupted by some noise, and so that the phone recognizer would be very inaccurate in that band, and so they would look at, the simplest thing is just to look at the predicted phone frequencies, and if they're very different from what you'd expect in the training data, then you say, well, this is a bad thing. They also looked at interphone arrival times because it's actually a time series,
Right.
and it turns out to be a regularity of natural languages that they have predictable interphone arrival times.
Yeah.
But those I think we need many more of those kinds of ideas to have some assurance that our test data is still coming from the same distribution. Like ideally, we would observe how the data is being collected and have our spies out there and say, no, they collected the data in a different way, so we can't trust the classifier. But we're rarely in a position to do that. Yeah. So, any other questions? Yes.
Quick question. So, in the reliability diagrams, so if we have a monotone pattern for the points on that, and we're trying to do, let's say, an isotonic regression for that. So, if that's the case, I'm not sure how we can do a better job on, let's say we have this loss function that we are trying to minimize,
Right.
we're looking for a threshold. So if we use that, the isotonic regression in this setting, we are saying that, let's say for example, any probability between 0.6 and 0.65, we're just going to call it 0.6.
Right.
Based on that isotonic regression.
Or 0.4.
Yeah.
Yeah.
Okay.
Yes.
So we are basically putting all of them in one group. But what if the perfect kind of threshold that we had was 0.62?
Right.
So in this case, we would do a better job if we use the predicted probabilities as is to optimize that loss function that we have.
Right.
In comparison to the case that we are actually doing the isotonic regression. I'm not sure.
Right. So if we actually, my second lecture was about predicting with a reject option. So if we're just trying to decide, let's say we have a target accuracy we want to achieve, 99% correct for all of our predictions, but we want the classifier to then reject everything that as much as it has to in order to achieve. Well, we really want to reject as little as possible of the test queries while achieving 99% correct on the ones that it actually classifies. And in that case, right, you can just use this same calibration data to tune the threshold on the original score, whatever it was. You don't need to calibrate it. And it's exactly the argument you're making there. Sometimes you're still better off learning to transform. But if it was monotonic to begin with, then you're totally right, that they're just equivalents. And the only reason to calibrate is that then, if I want 99% correct, I set the threshold to 0.99 and I'm done, right? But it's sort of like I've pre-tuned for every possible threshold in doing that. But if I have a specific threshold, then it'll take me a lot less data to tune for that one. I just have to estimate basically one Bernoulli parameter, the probability of accuracy, and I'm done. So I have a whole second lecture on what's understood for that. Yeah. Okay, well, I think we probably should get out of here. I think there's another class, so thank you for your attention.